Hi class, we are now on part 3 of chapter 15, the final portion of our special sense lecture. We are going to be covering hearing and equilibrium in this lecture. So we'll begin with the ear, the structure of the ear, since the ear is responsible for both hearing and balance. The ear has 3 major regions: the external or outer ear, which only is involved in hearing; the middle ear, or the tympanic cavity, which also is only involved with hearing; and then the inner or internal ear, which does both hearing and equilibrium. Receptors for hearing and balance respond to separate stimuli and are activated independently. So the external ear consists of 2 parts. We have the auricle or pinna, which is that flexible shell-shaped structure that surrounds the ear canal, and it functions to funnel the sound waves into the auditory canal. Then we have the external acoustic meatus, or the auditory canal. This is a short curved tube that goes through the temporal bone. It is lined with skin-bearing hairs, sebaceous glands, and ceruminous or earwax glands. It transmits the sound waves to the eardrum. And then there is the tympanic membrane, or our eardrum. This is the boundary between the external and the middle ears. It is a thin, translucent connective tissue membrane, and it vibrates in response to sound. And it transmits those sound energies to the bones of the middle ear. So how sound works is that sound, we're going to learn more about this, it comes in waves, and it's going to be funneled from the auricle or pinna into this external acoustic meatus, the canal, the auditory canal, and then it's going to vibrate the tympanic membrane. If you take a piece of paper and you talk against it, you'll feel it vibrate. So I encourage you to try that. Hello, 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 and it vibrates. And that's basically what's happening to the tympanic membrane. So here's a diagram. We have the external ear shown here with the auricle or pinna, this funnel-shaped external structure. It leads the sound waves, or funnels them, into this external acoustic meatus, which goes through the temporal bone. And then we get to the end of it is the tympanic membrane, or our eardrum. So the middle ear is the small air-filled mucosa-lined cavity in the temporal bone. Laterally, it's flanked by the eardrum, and medially, there is a bony wall containing the oval and round membranous windows. There's also a pharyngotympanic, or an auditory tube, that connects the middle ear to the nasopharynx. Formerly, it was known as the eustachian tube. It's usually flattened, but it can be opened by yawning or swallowing in order to equalize the pressure of the middle ear with the external air pressure. You do this when you're in an airplane. Your ears like pop your ears. So here we see the middle ear. We have the tympanic membrane. We have this area within the temporal bone, okay? And then it ends, we have this behind, there's 3 bones here. These are our auditory bones. We have the malleus, the incus, and the stapes. And the stapes is pressed up against a membranous window called the oval window. And then here's another one, which is the round window, okay? So when this presses in, it's going to press some fluid around, and then it's going to bulge this out, okay? And then we have this pharyngotympanic tube. This is what's normally flattened, and then we can yawn and open it up and equalize the pressure. This is also a reason why little kids will get ear infections. Their pharyngotympanic tube is more horizontal and less vertical, so it gets clogged up and infections can occur. So the auditory ossicles, those were the 3 little bones I was mentioning, and in the order in which sound travels through them is the malleus, or the hammer, the incus, which looks like an anvil, and the stapes, which looks like a stirrup that fits into the oval window. There are synovial joints between the 3 of them, and they are suspended by ligaments, which transmits the vibration from the eardrum through these 3 different bones into the oval window. All right, otitis media. This is a very common middle ear infection seen with children that often have a sore throat, especially those with shorter, more horizontal pharyngotympanic tubes. This is the most frequent cause of hearing loss in children. Acute infections form and they cause the eardrum to bulge outward and become inflamed. All right, so the last part of the ear is the internal ear. It's located in the temporal bone behind the eye socket, and it has both equilibrium and hearing receptors. There is a portion called the vestibule. It is an egg-shaped cavity of the bony labyrinth. There are two membranous sacs called the utricle and saccule that house the equilibrium receptor regions, and those equilibrium receptor regions are called the maculae. These two areas, the utricle and saccule, respond to gravity, changes in the position of the head, and linear acceleration. So if we look at the inner ear here, remember it starts at the oval window where the stapes is pressing into. This area is the vestibule, okay? In it, we have the saccule and the utricle, and then we have these two little areas called the maculae. These respond to linear acceleration and just changing the head in, in space, okay? So linear acceleration is if you hit the gas really hard and you went going fast in your car, or if you stopped really quick and you deaccelerated, okay? There are also semicircular canals which have to do with our equilibrium. They are oriented in 3 planes in space. At the base of each of these canals is something called an ampulla, and this houses the equilibrium receptor region called the Crista ampullaris. That area responds to rotational movements. So like if you were going to spin around circles. And in it, there is something called a cupula. That is like this jello-like material that's in the ampulla that moves. And when that moves, it bends hairs that allows us to know that we're rotating. So again, this was the vestibule. And then we have these 3 semicircular canals, and they're oriented in 3 different planes in space. At the base of them is the ampulla, like this bulgy region here. And then this purple area is the area where it's called the Crista ampullaris, okay? And the Crista ampullaris has the receptors for rotational acceleration or deacceleration. So again, all of the equilibrium receptors are found over here. We have the rotational equilibrium, which is done with the semicircular canals, and then we have the linear acceleration, deacceleration, which is done with the utricle and saccule. All right. Also in the internal ear is hearing regions, and this is called the cochlea. The cochlea looks like a shell, okay, or a snail. It is small, spiral shaped, and the whole thing, that whole shell, is the size of a split pea, so very small. It begins at the vestibule, and it contains a cochlear duct, which also houses the spiral organ, or the organ of Corti. So let me show you this. This is wrapped around like a snail. If we unrolled that and then cut through it, this is what we're gonna see, okay? So this is like cutting through it. And this is cutting through the cochlea. The cavity of the cochlea is divided into 3 areas. We have the scala vestibuli, the scala media, and the scala tympani. If we look at this, the scala vestibuli is this uppermost portion, and it is right up against the oval window. So remember, we have our 3 auditory ossicles, which are transmitting the vibrations from the eardrum. The last auditory ossicle is the stapes. It's right up against the oval window. It's going to be pounding against this oval window. On the other side of that oval window is the scala vestibuli that is filled with perilymph, which is a fluid, okay? So it's going to cause the perilymph to make waves. All right, so the scala media is this middle portion here. It contains endolymph, so it's filled with endolymph, and the spiral organ, or the organ of Corti, which is shown here in this box. And we're going to get into that a little bit more. And then there's also the scala tympani. The scala tympani is the portion that comes back and pushes against the round window and bulges out. Okay. And then we have the cochlear branch of cranial nerve number 8, vestibular cochlear nerve, and it runs from the spiral organ to the brain. So if we're going to look at, here's the cochlea. It goes all the way up to the top. See how it's cut like that? Each area of this cochlea has the 3 different parts of this, okay? and each little portion has a branch of the vestibular cochlear nerve going to it. So here we see this cut in half again. So the top part is a scala vestibuli. The middle part is a scala media, which has the spiral organ in it. And then the bottom part is the scala tympani. The scala vestibuli and the scala tympani both have perilymph. The scala media, or the middle part, the cochlear duct, has endolymph. So the spiral organ contains cochlear hair cells, and these are sandwiched between the tectorial and the basilar membrane. When the hair cells bend, they activate the neurons and send signals to the brain, which then interprets that as sound. So let me show you where this is. This is in the middle part, the scala media. We have this membrane. All right, so I don't know if this is the best time to say this, but I'll say it a few different times. We have the sound waves causing the eardrum to vibrate. That causes our auditory ossicles to then vibrate. That causes the last ossicle, which is the stapes, to vibrate against the oval window. On the other side of the oval window is the scala vestibuli, and this is going to go up the whole spiral all the way up to the top. At the very top, the scala vestibuli becomes the scala tympani, and then it rolls back down the other side, and the scala tympani bulges out the round window, okay? So it's weird. I'm going to show you another picture, which hopefully will help you understand it a little bit more. For different tones in our voice, or for sounds, so if we talk really low or we talk really high, it's going to go up a certain amount in the spiral. And that's how we can determine the tone of something. So if it's something that we hear, it goes up a certain amount. And this is what I mean by goes up, is that the waves of the perilymph are going to continue up to a certain point. And when it goes and causes those waves, it's going to cause waves in this endolymph and cause this vestibular or tectorial membrane, the tectorial membrane to vibrate. Okay, so let's go here. When the tectorial membrane vibrates because of the endolymph movement, it's going to bend these hair cells. When the hair cells bend, it activates the cochlear nerve, so cranial nerve number 8. So again, it's because of the movement of the fluid that's then going to move the perilymph is going to move the endolymph, which then causes this bending of the hairs, which then activates or creates an action potential in cranial nerve 8. Okay. All right. So this goes through the transmission of sound to the internal ear. So we have the tympanic membrane. This is our eardrum. When sound waves enter the external ear, it strikes the tympanic membrane, causing it to vibrate. This causes, the tympanic membrane causes the malleus to vibrate, which causes the incus to vibrate, which causes the stapes to vibrate, which presses against the oval window. Now the tympanic membrane is about 20 times larger than the oval window, so vibration transferred to the oval window is amplified about 20 times. On the other side of the oval window, we have perilymph in the scala vestibuli. That's going to be the way, it's going to cause waves in the scala, the perilymph in the scala vestibuli. That then causes waves in the endolymph in the scala media. And then that causes the perilymph in the scala tympani to also have waves. Sounds within our hearing range causes the perilymph waves to travel up the scala vestibuli, across the endolymph in the scala media, or the cochlear duct, and then down the perilymph in the scala tympani, thus then pressing out the round window. In the scala media, the endolymph waves move the membranes, which cause the hair cells to bend, resulting in action potential conduction along the neurons leaving those cells. And then the cochlear branch of the cranial nerve number 8 runs from the spiral organ to the brain, where it's then the sound is interpreted. This, I think, might help you understand this a little bit better. So here, I first want to mention that this blue part is the cochlea, but it's been unraveled. So remember, the cochlea looks like a snail. So now they've unraveled it, so now it just looks like a big long tube. So this shows the pathway of sound waves. We have sound waves coming in from the outer ear to the tympanic membrane, or our eardrum. It vibrates the auditory ossicles. The stapes is pressing against the oval window, which then causes waves in the scala vestibuli, okay? If the sound that is coming through is within our sound range that we can hear, or our hearing range, it crosses over at a certain point, causing waves in the endolymph of the cochlear duct. When those waves are going through the endolymph, it is going to bend the hairs. When the hair cells bend, it causes an action potential to be generated off of the cochlear nerve, and brings it off to the brain. And then also the waves continue down the perilymph of the scala tympani and press out the round window. If it is some sort of sound that our ears cannot hear, like a dog whistle or something that's like out of our hearing range, what happens then is that it still causes the vibrations to go all the way over to the oval window, up the scala vestibuli, but it does not cross over. It goes to the very end and then comes back down and presses out the round window. So because nothing crosses through here, nothing crosses the cochlear duct or the scala media, then no hair cells can be bent. If the hair cells don't bend, then we don't activate the cochlear nerve. And so we don't get an action potential there, and the brain doesn't interpret any sound. So when a sound comes that we don't hear, it takes what's called the helicotrema path. You see that up here. The helicotrema is like this area where the scala tympani and the scala vestibuli are where they meet. So the end of the whole snail-looking shell thing. Okay. Okay, so again, helicotrema path, waves with frequencies below the threshold of hearing travel through the helicotrema, which is the very end. They come through all this, go all the way to the end, and then down the scala tympani, and they never cross the scala media. Okay. Neural impulses from the cochlear cells, they reach the auditory cortex. Some fibers cross over, some don't. So both auditory cortices receive inputs from both ears. So here we see that cochlear duct and the activation of this cranial nerve 8 can go up into the medulla, up to, it can stop here in the inferior colliculi, which is the midbrain, go up to the thalamus, and then go to the auditory cortices. Okay. Here's a picture of the cochlea. It's pretty cool. Here's the hairs of the outer hair cells and the inner hair cells. Very cool. This goes through some of the different areas that we talked about. So the bony labyrinth, the membranous labyrinth, what happens in each of these. So semicircular canals, it does rotational equilibrium, and the Crista Ampullaris is the receptor region. In the vestibule, we have the utricle and saccule, and it does linear acceleration, and their receptor region is the macula. And then the cochlea, we have the cochlear duct, which does hearing, and the receptor region is found in the spiral organ of Corti. Okay, so hearing is the reception of a sound wave that is converted to a fluid wave that ultimately stimulates mechanosensitive cochlear hair cells that then sends impulses to the brain for interpretation. Sound is actually a pressure disturbance produced by a vibrating object and then propagated along the molecules of air. So let me explain that a little better. So, oops, where's my picture? Here we go. If we look at a tuning fork, so this is probably the best way to think about this as far as what sound is. If we hit a tuning fork, the tines of the tuning fork would vibrate left and right, okay? When they vibrate, they're causing molecules to get pushed together, and then when they go back the other way, there's an area where there's less molecules of air, okay? And this is what causes the waves. This is the airwaves, and these are going through your external ear into the tympanic membrane, okay? So sound waves are created when an object moves. The air molecules are pushed together. This is called the compression area. And then when the object moves back to its original position, there's an area of low pressure called rarefication, okay? Now, I showed you the tuning fork. The same thing is happening with your vocal cords or any other thing that we make sound with. So when I'm talking, it's my vocal cords which are moving, okay? So sound waves are actually alternating areas of compressions and rarefications. So compressed air molecules and areas of less air molecules. The object vibrating causes these waves to move outward in all directions. And this picture just shows it in going from one direction, but what really happens is it goes in all directions. So if someone's talking in the middle, you hear them from any direction, right? It's sound waves go in all directions. So some properties of sound you should be knowledgeable about. We look at two physical properties, frequency and amplitude. So the frequency is the number of waves that pass through a given point in a given time period. We look at the wavelength, which is the distance between two consecutive crests. Shorter wavelengths give a higher frequency of sound. So frequency is the range of human hearing, in the range of human hearing is 20 to 20,000 hertz. So a hertz is a wave per second. We're most sensitive between 1,500 and 4,000 hertz. Pitch is how our brain perceives those different frequencies. The higher the frequency, the higher the pitch. So here are two different sounds. We have the red one and the blue one. The red one, you can see, has up, down, blah, 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 blah. And we can see the blue one is a little bit slower, okay, because this is time, this is pressure. So the difference is that we have a higher frequency of wavelengths with the red one and then the blue one. So the red one is going to be a higher sound. Sorry, that sounds so stupid. A higher pitch. And then the blue one is going to be a lower pitch. One of them is not louder. It's just the pitch is different because of the frequency. Amplitude is how tall the crests are. This is perceived as loudness, and we measure loudness in decibels. The normal range is 0 to 120 decibels, with normal conversation around 50 decibels. Severe hearing loss can occur with prolonged exposure above 90 decibels. All right, so here we have the same pitch. Nothing is high or low. They're all the same, okay? It's just that this one, the blue one, is louder than the greenish blue one, okay? So the higher the amplitude, the louder it is. And again, this is in decibels. All right, equilibrium. So maintenance of equilibrium. Equilibrium is a response to several different inputs. So it is a response to movements of the head, which relies on our ears, eyes, and stretch receptors. The vestibular receptors do static equilibrium, and the semicircular canals do dynamic or rotational equilibrium. So static equilibrium in the vestibule, we have the maculae. We have one in the saccule and one in the utricle. It monitors the position of our head in space, and it plays a big role in posture. It responds to linear accelerations, but not rotational. So again, we're talking about these two right here, the maculae that are found in the utricle and the saccule. Again, they do the hit the gas really hard or hit the brake really hard, okay? How does the maculae work? Guess what? More hair. These hairs are what allows us to know, are we accelerating or deceleration? So these hairs are embedded in this like jello, okay? The jello has crystals on top of it, all right? So this jello-like thing is called the otolith membrane. And then the crystals are otoliths. The crystals help to hold the jello in place. So now if we were to lift our head up like this, then the jello would slide, and it would slide equally because we have all these otolith crystal things on top. When it slides a little bit, it bends the hairs in a certain direction. And then our brain can interpret those signals that are being sent by, as you can see, these little nerves to our brain. So whichever way this jello bends the hair cells, then our brain can interpret that, okay? So here's a close-up one. Again, this is in the maculae, so of the utricle and the saccule. So depending on how we move our head, this otolith membrane will move and bend these hair cells. The hair cells then send action potentials up those nerve fibers. All right, the Crista ampullaris has to do with rotational acceleration. So turn around in circles, okay? The Crista ampullaris has a place called the cupula. Let's go look at that. All right, I'm skipping some of this. So inside the semicircular canals at the base is the ampulla. The little purple part that's shown here is the Crista ampullaris. The Crista ampullaris includes this cupula, see that? And this will bend or move if you start rotating, okay? So if you start spinning around in circles, this gel, it's like more of a gel, it will then rotate and it causes these hair cells to bend, which then causes action potentials to be sent from these nerve cells, okay? Bending the hairs in different directions causes impulses of different frequencies. So the brain then determines or interprets those frequencies as how the head is rotating. Axis of the hair cells in complementary semicircular canal or semicircular ducts are opposite. So while depolarization is occurring in one, hyperpolarization is occurring in the other. So all that input is taken in by the brain, and then we can make a decision or an understanding of what is going on. So let me show you, this person's just standing still. The ampullary cupula is just hanging out there. And again, this is at the base of the semicircular canals. Once you start spinning one way, the endolymph inside here is going to bend the cupula in one direction. Then she stops, and then the endolymph flows back the other way, okay? So our body interprets all this movement. That's basically what this is saying. The equilibrium information goes to reflex centers in the brainstem to allow for reflexive responses to imbalance so we don't fall down. All right, motion sickness. We've probably all experienced this. This happens when the sensory inputs are mismatched. So our visual input differs from our equilibrium input. So a lot of times people will experience motion sickness when they're reading in a car. So your body's kind of bouncing around and you're getting equilibrium inputs saying that you're moving versus you're reading and it's telling you you're not moving. So there's this disconnect there. The conflicting information causes motion sickness. Warning signs are excessive salivation, pallor, rapid deep breathing, profuse sweating. Treatment is with anti-motion drugs that depress the vestibular input, such as meclizine and scopolamine. Oops, sorry. Okay, tinnitus. Tinnitus is another, or tinnitus. I've heard it say both ways, but this is the ringing, buzzing, or clicking sound in our ears in the absence of auditory stimuli. So this can be due to cochlear nerve degeneration, so getting older, the inflammation of middle or internal ears, and also the side effect of aspirin and other drugs. Other homeostatic imbalances that I'd like you to know. There's two types of deafnesses. There's conduction deafness and then sensory neural deafness. Conduction deafness is caused by the blockage of sound conduction to the fluids of the internal ear. So this would be, say there's a bunch of earwax, so the sound waves can never vibrate your eardrum. Or there's a perforated eardrum, so when it vibrates, it doesn't move the auditory ossicles. Or it could be otitis media, some sort of infection, or otosclerosis of the ossicles. So they're not vibrating to the inner ear. Okay, so some sort of blockage, conduction deafness. Or we have sensory neural deafness. This sort of deafness occurs when there is damage to the neural structures at any point from the cochlear hair cells to the auditory cortical cells. So all the movements, all the fluid movements, the vibrations, they're all occurring. There's just some sort of damage with the neural end of things. And this is typical from gradual hair cell loss. Excuse me. Okay. And that is the end of chapter 15. If you have any questions, make sure to contact your instructor. Have a great day.